This is a summary of both some of the concepts and methodology associated with calculating stomatal and non-stomatal limitations to photosynthesis. In the literature, you'll sometimes see these concepts referred to as gas phase and mesophyll limitations or resistance or conductance, depending on how old the literature is and so on. Now, generally, we speak about these phases as conductances rather than as resistances. And you'll either see them referred to as gas phase and mesophyll conductance or stomatal and non-stomatal conductance. I'm going to use a paper written by Hamlin Jones a long time ago, but I think it's a valuable paper that summarizes a number of approaches to doing these calculations that I think also help with conceptually understanding what these conductances or resistances mean, especially relative to ACI curves. So we'll be focusing on that paper. Sort of starting with the cross section of the leaf, just to remind you, we're talking about leaf mesophyll. This is where most of the chloroplasts are located in the leaf, and intercellular spaces, and of course, stomates in the leaf. So we're going to zoom in on this part of the leaf here. And this diagram from Park Nobel's book, I think, also does a good job of talking about the resistances we're dealing with here, resistances or conductances. We're talking about gas phase resistances or conductances, which basically go from the boundary layer around the leaf through the stomata and into the intercellular spaces, and then the mesophyll or non-stomatal components, which are basically when the CO2 molecule needs to move through the cell wall, through the cell membrane, through the cytosol or cytoplasm, through the chloroplast membrane, and then across the chloroplast stroma. So those can sort of be summarized by this green part. That's these components. That green part is the gas phase or stomatal limitation. And then once that CO2 molecule reaches the cell wall, those are the mesophyll conductances or resistances. So conceptually, those are the two pieces that we're talking about. We're talking about gas phase and mesophyll conductances or resistances. Now, all of these calculations are based on ACI curves. So to understand these calculations, you need to make sure you're solid on the concept of an ACI curve. So that's net photosynthesis rate plotted against CI, leaf intercellular CO2 concentration. So CI just refers to the CO2 concentration basically right outside the cell wall, so in the intercellular spaces. So how does net photosynthesis respond to CO2 concentration in the intercellular spaces? So if we were to measure net photosynthesis rate just on a leaf under some conditions, let's say that measurement we take is A1. That's going to sit somewhere on this ACI curve. And there will be some CI, which in this case would be about 200. So when we measure net photosynthesis rate, usually at saturating light, we'll get a net photosynthesis rate and a CI. So this would be the calculated CI. Our measurement actually is taking place, that leaf is in some ambient CO2 concentration. So right now, the ambient CO2 concentration in the atmosphere is about 410 parts per million or micromoles per mole. But of course, because there are stomatal limitations, the CI, the CO2 concentration inside the leaf, is below the ambient CO2 concentration outside the leaf. So at any rate, this is sort of that operating point that A, or net photosynthesis rate, at some ambient CO2 concentration. So, and this line, the supply function, is basically a line connecting ambient CO2 concentration to that photosynthesis rate that we measured. This slope, the slope of this line, the negative slope of this line, is essentially the stomatal conductance. So the steeper this slope, or the steeper this negative slope, the wider open the stomata are, the greater the stomatal conductance. And as the stomata open, photosynthesis rate will move up this curve. As stomata close, the negative slope of this line becomes smaller, and A, or photosynthesis rate, will move down this curve. Okay, so that's how ACI curves work. All right, so let's take a look at an ACI curve and imagine a hypothetical situation. So the hypothetical situation is, okay, we have ambient CO2 concentration here, about 390. You can tell this graph was made a number of years ago when the ambient CO2 concentration was lower. But at any rate, let's say the ambient CO2 concentration is 390. But we're going to imagine a situation where the epidermis of the leaf is gone and ambient CO2 concentration, the cell wall, the chloroplasts, are exposed to, or the mesophyll cells are exposed to a CO2 concentration equivalent to ambient CO2 concentration. Essentially what that means, if those cells are exposed to ambient CO2 concentration, that means there's no gas phase limitation, right? No, I imagine a situation with no epidermis. So those mesophyll cells are exposed to that ambient CO2 concentration. Based on the ACI curve for this leaf, if that situation happened, this would be the net photosynthesis rate that you would see. So A2 is basically a hypothetical rate of net photosynthesis if there was no gas phase limitation. In other words, if there were no stomata holding the CO2 back, those cells would be exposed to ambient CO2 concentration, and the net photosynthesis rate would be A2, okay? But in reality, when we measure net photosynthesis rate of that leaf under that ambient CO2 concentration, we actually get A1. That's the measured net photosynthesis rate. So this is the measured net photosynthesis rate. But once we have an ACI curve, we can extrapolate to this theoretical net photosynthesis rate, which is the net photosynthesis rate if there were no gas phase limitation. What that does then is allows us to calculate LG, that's gas phase limitation. This is method 4 from the Jones 1985 paper. So that gas phase limitation is basically A2 minus A1 divided by A2. So what you can see is that is A2, which is that maximum rate of net photosynthesis without gas phase limitations, minus A1 divided by A2. So this difference in net photosynthesis rate is the limitation due to gas phase limitation. So it's basically how much is net photosynthesis reduced due to that gas phase limitation. So to me, this is a fairly intuitive estimate of gas phase limitation. I can sort of imagine this situation with no gas phase limitation. And I know that when gas phase limitation is in place, this is the net photosynthesis rate. So this difference is due to gas phase limitation. So this will be some percentage, some fractional reduction in net photosynthesis that's due to gas phase. So that'll be a number between 0 and 1. So that's a nice, to me, intuitive estimate of gas phase limitation. All right, here's Jones's method 5, which is looking at two resistances that are related to either gas phase resistance or mesophyll resistance. So we've got our ACI curve here, and we've got net photosynthesis rate right here. It's the operating point. This is net photosynthesis rate measured at some ambient CO2 concentration. So that's right here. And we have some CI associated with that, okay? This is ambient CO2 concentration. Again, this is a graph was made some time ago when ambient CO2 concentration was about 390. And we know that the line connecting ambient CO2 concentration to that operating point, that's the supply function. And we know that supply function is the negative of that is related to stomatal conductance. So the negative of that is related to 1 over gas phase resistance. So this term, negative 1 over Rg, the slope of this line is negative 1 over Rg. So if you calculate this slope, multiply it by negative 1 and invert it, you can solve for Rg. So that's gas phase resistance. Okay. And then this term, the slope of this line around that operating point is basically a gas or a non-gas phase conductance. So remember, the slope of this line at the operating point, when we talked before, is related to VC max, which is the maximum rate of carboxylation of Rubisco. So this is essentially the biochemical conductance. So the inverse of that slope is the mesophyll resistance. So it's the resistance to the mesophyll uptake of CO2. So if this slope gets steeper, that means there's less resistance to gas uptake in the non-stomatal components, or there's a greater conductance. Okay, so this slope, this line, is related to those non-stomatal or mesophyll components, and the slope of this is related to the gas phase or stomatal components. So Jones says, okay, the way that we can use these to calculate gas phase resistances or the limitation due to the gas phase component is to look at the total resistance, which is Rg calculated from this slope, and Rm calculated from this slope. That's the total resistance. So if you look at my previous diagram, which showed the green arrow and the blue circle, those two added together is the total resistance. And do Rg, there's just the gas phase resistance divided by the total resistance. That'll tell you then what fraction of that total resistance is due to the gas phase. And again, that'll be a number between 0 and 1. Jones likes this method for a couple of reasons. One is because it doesn't involve extrapolating gas phase to some theoretical, like our previous method did. Our previous method involved, this theoretical A2, which really never exists. So he likes this one because it's at the operating point. Another reason he likes this is because this is relatively easy to calculate. We actually don't need to measure an entire ACI curve to calculate these. All we need to do is measure photosynthesis rate at the operating point. So essentially, you'd measure light saturated net photosynthesis rate, which is A, and then basically measure net photosynthesis rate at a couple of CO2 concentrations above that and a couple of CO2 concentrations below that, and then fit a linear regression through those points, and that will give you the slope of this line. So sometimes when I'm advising folks and they're interested in calculating gas phase resistances, I'll suggest that they use Jones method 5 because it really only involves measuring net photosynthesis rate at 5 or 6 CO2 points. So you basically measure net photosynthesis rate at the operating point, and then you step up your CO2 concentration, maybe 20 or 30 parts per million above that for a couple of points, and then 20 or 30 parts per million steps below that for a couple of points. And then you've got what at that point will be a relatively linear line that you can use to then calculate this slope, which you can use to calculate RM. And then you'll calculate RG based on the slope of this line at the operating point.